Hello, discrete math fans. Let's prove that this identity is true for all n in the natural numbers. So the left-hand side will have the sum, where k goes from 1 to n, of 1 over 2k minus 1, 2k plus 1. And the right-hand side will be n over 2n plus 1. We're going to prove this with induction. So let's let p of n be the predicate that's marked star. All right, that's a little bit of laziness for you, so we don't have to rewrite that whole equation again. Now on the left-hand side, if we have n equals 1, then there's only one term in the sum, and that one term will be 1 over 1 times 3. And then the right-hand side would be 1 over 2 times 1 plus 1. Those are equal, so p of 1 is true. Now let's let n be a natural number, and we'll assume that p of n is true. Again, we're assuming that it is true for a particular but arbitrarily chosen value of n. So we are assuming this particular integer sum. And again, n is a fixed integer. We're not saying that it's true for all n, we're saying it's true for some particular n. Now we want to show that p of n plus 1 is true. So now the integer sum that we want looks like this. So on the left-hand side, we're stopping at n plus 1, and on the right-hand side, instead of n over 2n plus 1, we're going to have n plus 1 over 2 times n plus 1 plus 1. Let's go ahead and start with the left-hand side. We'll manipulate that and try to get to the right-hand side. Along the way, we'll mark clearly where we use our inductive hypothesis. All right, so we're starting with the sum on the left-hand side, where we go up to n plus 1. Now what we're doing here is we're peeling off the last term. Now the book goes through some discussion of how to do this, how to take a sum that goes from 1 to n plus 1 and peel off the last term, or how to put it back in. It'd be well worth your time to go read how that works. Take note that the sum, this is the sum, and that goes up to n, and then this is the extra term because we're going up to n plus 1. And if you like, we'll do a little simplification of the term on the far right. It looks like 1 over 2n plus 1, 2n plus 3. Okay, now let's keep going. Here comes the key step. We're going to replace that sum with n over 2n plus 1. Why can we do that? That's our inductive hypothesis. Our inductive hypothesis said that the sum, where k goes from 1 to n, of 1 over 2k minus 1, 2k plus 1, is equal to n over 2n plus 1. Now from here on out, it's just going to be some basic algebra. In fact, let me just show you all the steps at once. You can work out for yourself how all of this goes. Essentially, it's a common denominator and factoring and piecing things together. Notice at this last stage, we're going to cancel out a 2n plus 1. Let's go on to the next step. So to complete the algebra, we finally arrive at n plus 1 over 2 times n plus 1 plus 1. And remember that this was exactly the thing that we wanted to get. Therefore, p of n plus 1 is true. And finally, by the principle of mathematical induction, p of n is true for all n in the natural numbers. And this is what we've been trying to prove. Okay, that's all for now.